if that's okay with you.
Yeah, sure.
Sure. So it's a pleasure to have Waseem Bakr speaking today. I'll say a bit about his CV. So he was actually an undergrad at MIT and then joined for his graduate program, graduate time. He joined Marcus Greiner at Harvard University, and there he really worked like on quantum gas microscopy and investigating Bose-Hubbard models. And for example, like observed the superfluid to Mott insulator transition. And then I guess his trajectory took him back to MIT for a postdoc with Martin Sweerlein. And after that, since then, he's been a professor at Princeton working on strongly correlated materials and simulating them, again, with ultra-cold quantum gases. Waseem has received a number of prizes, for example, like the AAS Newcomb Cleveland Prize in 2011 and the AMO Prize for outstanding work for his dissertation in 2012. And today we'll hear him on his latest work on exploring non-equilibrium dynamics in novel Fermi gas systems. Waseem?
Yeah, thank you, Valentin, for the introduction, and thanks for the invitation to speak here at ITAMP. So I'm going to be telling you about two experiments we're doing with very different platforms. One is Fermi Hubbard systems in a tilted optical lattice, and the other is going to be Rydberg-dressed fermions. So at first glance, these look like very different systems, but the common theme here between those two is that their Hamiltonians are both describing kinetically constrained systems, which can lead to some very interesting dynamics. And I thought this would be a good topic to cover with this audience, because I know there's at Harvard a lot of interesting studies of dynamics in the group of Misha Lukin and Marcus Greiner, where they're studying the effects of things like kinetic constraints and disorder on the dynamics of systems and how they can break thermalization. So it looks like a small audience, so please feel free to interrupt at any point with questions. Okay, so the lens I want to look at these experiments through is the lens of thermalization. So we know thermalization is a process by which systems reach thermodynamic equilibrium, where is basically you have a state where there are no net flows of matter or energy, and memory of the initial state is completely erased. And this occurs on all sorts of length scales, of course, in physics, from the evolution of the early universe to like more mundane systems, like here I'm showing milk pouring into a coffee cup. And it's really important to understand this topic because thermalization really forms the basis of the foundation of statistical mechanics. So one topic that has grabbed a lot of attention in recent years, both on the theoretical front and experimental front, is thermalization in closed quantum systems. And the question one poses here is, how do you reconcile unitary quantum evolution with thermalization in isolated quantum systems? So what I want to think about here is experiments where we start with some sort of very patterned initial state that has a lot of information in it. So schematically, this is going to be the sandcastle. Just imagine for a second, it's a quantum sandcastle. And then we're going to do a quench on the system. So let's say the wave comes by and it hits the sandcastle. So then the sandcastle will evolve in time, and after a long time, it's going to reach some state of thermal equilibrium, where you can describe the state in terms of a few thermodynamic variables, like, let's say, temperature or chemical potential. So this is the late time state. So the paradox here is it seems you need very little information to describe this final state, but you know that we started with this initial state that has a lot of information, and the dynamics is this unitary dynamics, which is reversible. So you could imagine just reversing the unitary dynamics and recovering the sandcastle. So clearly the information has not been lost. It's just, it's hidden somewhere. And so the resolution of this paradox is this idea that has been introduced recently of quantum scrambling, where essentially this quantum information is scrambled into non-local degrees of freedom, which are no longer accessible easily with experimental probes. So essentially, you can think of thermalization in isolated quantum systems to be the result of the spread of entanglement in these systems. And if you go and look at any particular subsystem, then these subsystems, when you do local measurements on them, the measurements will agree with the predictions of statistical mechanics. Okay, so this is thermalizing systems, but there's been a lot of interest in recent years with looking at systems that fail to thermalize, both on the theoretical front and the experimental front. And of course, cold atoms are an ideal playground in which you can explore failure of thermalization because you have these very isolated quantum systems. And on a course level, you can think of systems as being classified into either thermalizing or non-thermalizing. But if you want to go into even more detail, these non-thermalizing systems can be kind of sorted into universality classes, if you wish, for the dynamics. And I'm going to mention 4 such classes. So the first is one that has been studied actually in cold atoms quite a while back, these integrable systems. So there's these famous experiments from the group of David Weiss with a one-dimensional Bose gas, which is integrable. So there's lots of conserved quantities. And this system fails to thermalize in the usual sense. So it would thermalize to what's known as a generalized Gibbs ensemble that's consistent with the conservation laws. And these are rather fine-tuned systems. So if you introduce perturbations to them, as was done, for example, in this work from Ben Lev, you can easily sort of destroy the integrability. Now, there's another class of systems, which, for example, is being explored in a group of Marcus Greiner, and also in experiments from in Munich. These are these disordered quantum systems, which are strongly interacting. And there you have a more robust form of or more robust failure of the thermalization. These are called many-body localized systems. And these arise, as I said, due to the disorder in the system. And you have an emergent conserved quantities in the system, an extensive number of them. Okay, so you could also look for things in between. So there are these very nice experiments that happened recently in the Lucan group, where they discovered many-body quantum scars. These are basically systems where you have not the whole spectrum is local, like these local MBL experiments, nor is the whole spectrum thermalizing. It's somewhere in between. So what you have is a few non-thermalizing states embedded in the huge, exponentially large Hilbert space that's thermalizing. And this was observed in these experiments on Rydberg atom chains, where they see basically oscillations after a quench that are there for a long time. Okay, so this is what's called quantum many-body scars. I want to discuss today a 4th robust way of creating non-thermal systems, namely this Hilbert space fragmentation idea. So this is an idea that has appeared in theoretical works in the last couple of years, and there haven't been any experiments in that direction. So it's very analogous to quantum many-body scars, except that instead of having just a few non-thermal states in the Hilbert space, here you have an exponentially large number of them. Okay. So usually the way you engineer Hamiltonians that exhibit this Hilbert space fragmentation, and also for the quantum many-body scars, is you have systems where you have kinetic constraints that restrict what can happen in the dynamics. So we're going to essentially imagine a small number of conservation laws. Typically, this is going to be 2 in the experiments I'm going to describe. And then we're going to combine that with the locality of the Hamiltonian. So the interactions are going to all be local. And this sort of interplay between the locality and the conservation laws is going to lead to a very fractured Hilbert space. So the conservation laws lead to some super selection laws. So you have like basically chunks of the of the Hilbert space that can be labeled in terms of the conserved quantities. So those obviously don't change during the dynamics. But then even when you look within one of these sectors, it further divides into an exponentially large number of dynamical sectors. And these subsectors are all disjoint. They come in varying sizes. You can have small subsectors just of size 1. Those would be frozen states. You can have much larger subsectors where you can have some dynamics. But the interesting regime is you can create these systems where this fragmentation is known as strong fragmentation. And in that case, if you take a look at a sector like this one, and you look at the largest subsector, the size of the largest subsector compared to the size of the sector becomes exponentially small as you increase the size of the system. So it's exponentially small in the size of the system. And this leads to non-ergodic behavior. So if you start with a generic state, it's going to have projections on all these subsectors, and all these projections can't thermalize because of the small size of these subsectors. So this is quite generic behavior in these fractured Hamiltonians or fractured Hilbert spaces. Just as a disclaimer, we haven't observed any of this non-ergodic behavior yet. What we've been working towards in my lab is trying to engineer Hamiltonians where one can create the constraints that are required to realize this Hilbert space fragmentation. Okay, so just to kind of make these abstract ideas a bit more concrete, I want to go into a specific example. So this is an example that was introduced in the first paper on fragmentation from Frank Pullman's group, and also there's a related work from Kimani and Nand Kishore. So there they considered a spin Hamiltonian. So imagine you have a spin chain, and it's going to be a spin 1 chain. So on each site, you can be +1, 0, or -1. This the projection of SZ along of SZ. Okay, so now this Hamiltonian has 3 side terms. So it has range 3. And what it does is it lowers the middle spin by 2 and then raises the left and the right spin by 1, or does the Hermitian conjugate process. So this type of Hamiltonian conserves 2 quantities. The first quantity is what we call the charge. So this is the terminology they use in these papers. So the charge is basically here we're referring to the total SZ of the chain. And then there's the dipole moment. This dipole moment, you basically are summing over SZ and then multiplying by the index and of each site. Okay, so you can reference this to an arbitrary site. So these 2 are conserved by this Hamiltonian. And what this gives rise to is something called fractonic dynamics. So these fractons are basically systems where you have excitations, and the single particle excitations are immobile, but pairs of excitations are mobile. So here's an example. So if you start with all of the spins in the state 0, and then you embed a charge +1, then this charge, if you try to move it around, well, that conserves the charge, but it doesn't conserve the dipole moment as you move around, okay? So the single charge is stuck. And then on the other hand, if you start with a dipole, this can move around freely because it will conserve in its motion Q and P. Okay, so what are the interesting things about such Hamiltonians? Well, one thing is they have an exponentially large number of frozen states, or scars, quantum scars, if you wish, in the language that was introduced to describe the Lucan experiments. So, you can construct them explicitly. So this is a Hamiltonian with range 3. So it's natural to consider sort of chunks of 3 of like 3 plus charges or 3 minus charges, or you can make the chunks even bigger. And if you just sort of pattern any state with alternating like pluses and minuses, there are 2 to the L/3 such states you can create, and all such states are frozen. Okay, so you can see that if you take, like, let's say this piece here, and act on it with a three-side Hamiltonian, then this cannot go anywhere because this is a state with extremal charge, all pluses. And since the charge is conserved, the Hamiltonian won't reconfigure this. Now you can also take a section like this one here, spanning a domain wall, where you have, again, the Hamiltonian can't do anything about the state, because if you look at the dipole moment for the given Q that you have here, this dipole moment is again extremal because all the pluses are on one side and all the minuses are on one side. So it's a state of large extremal dipole moment for the given charge. So these types of states are completely frozen. Okay, so that's one interesting thing. But then the more interesting thing is that actually the Hilbert space is, as I mentioned, strongly fragmented. So if you look at, let's say, any particular sector, let's say the sector with, here they were looking at in this paper, the sector with Q equals 0 and P equals 0, and you identify the largest dynamical subsector in it, the ratio of the size of that subsector to the size of the sector is exponentially small in the size of the system. So this is true for a Hamiltonian of range 3. You could also imagine going to a Hamiltonian with, say, range 4, acting on 4 sides, again respecting the dipole and charge conservation laws. And in that case, you find the system is no longer strongly fragmented, but it is actually weakly fragmented in the sense there's only a few non-thermal states, not an exponentially large number of them. So this blue stars here, where basically the size of this largest subsector is almost the whole sector. Okay, any questions so far?
So is this like kind of strongly connected to this being a 1D system, or like?
No, those can be in 1D or 2D. So I'm going to show later examples where you can have dipole conservation laws in 2 dimensions, like the dipole along X and Y can both be conserved.
Mm-hmm. Okay, and this would also work with like a 3, like with these Hamiltonians that involve 3 terms.
Yeah. Mm-hmm. Okay, so now let me move on to the experiment. So I'm going to basically show you how we can engineer Hamiltonians with such constraints in the hopes of eventually studying non-ergodic dynamics with them. And the experiment is going to be an experiment with a microscope. So you're probably familiar with these experiments from the work going on at Harvard and Marcus Greiner's group, and at MIT and Martin Zwerlein's group. So basically we have these experiments where we can prepare degenerate Fermi gases in 2 dimensions. This is a gas of lithium-6 atoms. And we can resolve with these microscopes the individual atoms and their spin states. So they're very nice systems in which to study Fermi Hubbard physics, and there's been a lot of beautiful work recently studying the interplay of spin and charge correlations in these systems in the context of Fermi Hubbard physics. For the purposes of this talk, I'm not really interested at all in the fermionic character of the gas. Okay, so we're going to just focus on the dynamics, and everything I say is sort of not related to the fermionic character. Okay, so let me start first by telling you how to engineer Hamiltonians that are very similar to the Hamiltonian that was considered by the Pullman group in the paper I described. So we're basically going to realize these kinetic constraints in the system by going to a Fermi Hubbard model and then introducing a very large effective electric field, or if you wish, it's just a tilt in the optical lattice. Okay, so I'm going to describe how that gives rise to these Hilbert spaces that are fractured. Now, in the actual experiment, we haven't started exploring that regime yet, but we've explored a different regime where we see thermalizing states, but the thermalization turns out to be really slow. I'd like to explain why this thermalization is so slow. So basically, we're going to have hydrodynamics in the system. It can reach local thermal equilibrium, but the hydrodynamic description involves an interesting interplay between charge and heat transport in the system, which actually leads to a slowing down of the thermalization. Okay, so this is described in this paper in PRX. Okay, so the basic Hamiltonian here is the Hamiltonian of the Fermi Hubbard model. So I'm sure a lot of you are familiar with that. So it's basically you're going to have tunneling between neighboring sites in an optical lattice. So we're going to put two species of fermions there. We're going to call them spin up and spin down. The fermions can tunnel between neighboring sites, and then if you have two fermions of opposite spin landing on the same site, you get a strong repulsive interaction in the system. So now the new ingredient we're going to add is a large tilt. Basically by large here, I mean that the bias between neighboring sites, F, is going to be on the order of the tunneling and the interactions. So basically the Hamiltonian is the Fermi Hubbard Hamiltonian minus F times the position operator. And the physics of this system is well understood in the non-interacting case. If you just put a single particle in a tilted potential, that's just the physics of Bloch oscillations. So as you increase the tilt, the amplitude of the Bloch oscillations gets smaller and smaller in real space. And basically at some point when F is comparable to the tunneling, the amplitude of these oscillations is on the order of one lattice site, and you can start talking about stark localization in the system. So this is, very well understood, but then until recently, surprisingly, it was only until recently that people started to explore what happens when you have an interacting system of fermions in a tilted potential. And this was described in these papers here. So the inspiration was, so the question that they're posing is, can the single particle localization persist? Can we have a many-body version of this localization, the stark localization? And so this is in analogy to what happens with Anderson localization when you have disordered systems. So there, when you introduce interactions, we know we have this phenomenon of many-body localization, where even in the presence of interactions, the localization will persist. Okay, so first there were claims of, in these papers, of MBL in clean tilted systems. What they did in these theory papers was start from some particular initial states and simulate the dynamics, and they saw that these states failed to equilibrate. It turned out in later work, follow-up work this year, that it's not quite like MBL. So in MBL, the entire spectrum of many-body eigenstates are localized. Here, it's only some states are localized, others are thermal. So this is actually turns out to be more in the spirit of this Hilbert space fragmentation I was discussing. So you have this fractonic physics where the charge and the dipole are conserved, and you have an exponentially large number of localized states. So let me just discuss this first in a 1D tilted system to show you how it kind of maps to the Hamiltonian that I was introducing earlier. So we have these constraints of charge and dipole conservation. I mean, obviously the number of particles is conserved in the system. The dipole conservation, that comes about because of the tilt. So essentially the tilt is enforcing energy conservation. In the presence of the tilt, if you just put a single particle and the tilt is very large, clearly the particle can't hop up or down because the system doesn't have any dissipation. It's a closed, isolated system. So since the tilt energy is large compared to the tunneling energy, this particle is just stuck. But then if you put two particles, you can have one particle go up and the other particle go down. And that would then conserve the energy and hence the dipole. So the moves in this Hamiltonian are local. They're mediated by the interactions. So the typical sort of process that you can have is something like the one I'm showing in this diagram. So let's say you have the tilt pointing down this chain. So we can consider these three sites, and you can have the red fermion hop up and the blue fermion hop down. That would conserve dipole moment and charge. Basically the range of this process is 3. So this is starting to link to this earlier spin Hamiltonian I was describing. So now these constraints of dipole conservation, it's only strictly true in a single band system in the limit of infinite tilt. So of course, in a real system, we have many bands. And if you start to increase the tilt too much, then you have to worry about multiband physics. But if you focus on the single band system for a second, then you still need the tilt F to be very large compared to T in order to have strict dipole conservation. You need to go to the infinite F over T limit. If you have a finite F over T, then you can only talk about sort of the conservation of the dipole up to some prethermal time scale. So this is now, you talk about a prethermal regime where you can get this effective range 3 Hamiltonian that conserves the dipole moment. And the time over which this conservation holds is exponentially large in the ratio of F over T. So basically you can do perturbation theory in T over F, and the first sort of process that appears is the one that I described here. So this appears with a matrix element that's something like T squared over F squared U. And then we have to worry about this time scale. And then there's a second time scale that one has to worry about, which is when you go to a longer time, there are these higher terms in the perturbative expansion that kick in, which are essentially longer range terms. So those are like range 4, 5, etc. And those scale in the following way as outlined in this paper. So basically, the minimum of these two time scales is the time scale which determines the time over which you can hope to observe strong fragmentation. Because as I said, when you go to these longer range terms in the Hamiltonian, those take you out of the strong fragmentation regime. So you both need to only have this short range 3, and at the same time, the dipole conservation to hold. Okay, so there was a question earlier, is this only true for 1D? It's true for 2D, but then you would have to apply the gradient along some irrational angle. So you don't want it to be along the lattice axis, nor to be some sort of special case like 45 degrees. It needs to be some sort of arbitrary angle. And then you'll conserve both dipole along X and dipole along Y and the charge. And then you can get the same sort of fragmentation physics. So in our experiment, we actually started by aligning the tilt in a 2D system along one of the lattice axes. And it turns out in that case, what you get is thermalizing physics, not Hilbert space fragmentation. But as I said, this thermalization is rather anomalous. So the experiment goes as follows. So we're going to put this two-dimensional quantum gas in here. That's this small square here. We're going to put it in on the slope of a large Gaussian laser beam. That's the red beam you're seeing here. And so it's going to experience this large tilt potential. And we align it so that the tilt potential is along the x-axis. Do you guys see my cursor? Yeah. Okay. So it's along this x-axis here, and then along the y-axis, the fermions are free to tunnel around. So that's why the system thermalizes, because there's a large Hilbert space in the direction orthogonal to the tilt where the fermions can move in this large Hilbert space and can thermalize. Now, since the fermions can move in that direction, we really need to put hard walls to prevent them from just escaping during the dynamics. Okay, so now it's time to build this quantum sandcastle. So we're going to start with this initial pattern state that has all the information in it. So we're going to create a charge density wave in the lattice with a period typically on the order of 20 sites or so. And then we're going to do the quantum quench by removing the potential that creates this pattern. And so what's going to happen now is we'll undergo this thermalization process where at the end, the system has reached some state of thermal equilibrium with a given T and a given temperature and a given chemical potential. It's a uniform density. Okay, so this thermalization, as I was discussing, is slow. And the way we characterize this is we track the amplitude of the oscillations, the amplitude of this charge density wave versus time. And we find that it decays exponentially. So now we're going to look at it in two cases. So first, let's look at it in the case of moderate interactions, U over T4, and we're going to have no tilt potential first. So this is kind of the easy case. If you don't have a tilt potential, you just expect diffusive dynamics in the system. And indeed, that's what we see. So if you fit these exponentials, they fit to a time scale tau. And if we vary the wavelength of the charge density wave, so these different curves are different wavelengths, we find that the relaxation time scale goes as the square of the wavelength, which is exactly what you would expect from diffusion, okay? So next, let's try putting in a large tilt. So now we're going to go to F over T2. And again, these moderately strong interactions. And now what we see is the dynamics is a lot slower, as you would expect in the presence of a tilt. But the interesting thing is how this time scale goes with the wavelength. And now the exponential decay time, tau, goes like the fourth power of the wavelength. And this is essentially indicating subdiffusive charge relaxation. Okay, and subdiffusion is something that doesn't occur very often in nature. So one way you can get it is through fractons. So they often exhibit subdiffusive dynamics. Okay, so why do we have this subdiffusive dynamics? Well, actually, before I show you why, let me just show you that, of course, we can interpolate between these two regimes by changing the gradient. So if you scan the gradient now from 0 to a large value, you look at how this time scale scales with the wavelength. So it's a power law, wavelength to alpha. And this power law goes, this exponent alpha goes from 2, the diffusive case, to 4, which is the subdiffusive case. And the transition happens roughly at around F over T1. Okay. Okay, so how do I understand what's happening here? So we need to understand the thermalization process, which occurs on a long time scale. So essentially, we're going from this charge density wave to some uniform state. And before I describe the late time dynamics, it turns out there's actually something interesting happening at short times in the system. So the first thing you might expect is if you put a system in a gradient, it might want to fall down the gradient, okay? Now, I already told you this doesn't happen in a tilted system because of the energy conservation of the isolated quantum system, but actually it does happen, but just for a small displacement, okay, on the order of 1 lattice site or so. And the way to understand this is essentially the system wants to fall down and exchange the tilt energy with internal energy. So you can take energy out of the tilt energy and put it into internal energy of the system. But you can only pump so much energy into the internal energy within a single band system. So basically, you're trying to maximize the entropy of the system during thermalization. So you're going to try to heat the system to infinite temperature within the single band. And then in this infinite temperature state, you have a bound on the energy. This infinite temperature state has an amount of energy in it, which is on the order of the couplings U and T. So you can only store so much energy in the system. And from that point on, you can't transfer any more energy from the tilt into the internal energy. So how much tilt energy can you transfer? Well, you would compute that by saying F, the bias between sites, times delta X, the distance by which you drop, has to be on the order of the energy that you can put into the internal energy, which is kind of like T or U. And since these two quantities, the T and the U and F, are all in the same order, you realize that this drop has to be at most on the order of 1 site. And that's indeed what we see in the experiment. If you look at the phase of this wave, it drops by on the order of 1 lattice site, okay? So that's the first step. So basically, in the process of dropping, you heat up to infinite temperature in the system. Now, here I'm talking about on average in the system, we have an infinite temperature because we still haven't thermalized completely. We still have this modulation in the system that we need to get rid of to thermalize. Okay. So since we're talking about infinite temperature, it's more natural here to talk about the inverse temperature, beta. And in this case, basically, we have beta equals 0 on average in the system. but we have oscillations of this beta about 0. And the way to understand this is we still have this oscillation of the density that you see here in green. And once we undergo the local equilibration in the system because of these chains orthogonal to the tilt, now you can talk about a local beta in the system. And you can understand the local beta for, so you have this variation of the density in a tilted system. And you can sort of identify a local beta at every point, which is this orange curve here. So if you look at this section here where the density is increasing in the system as you go to higher tilts, then you have a situation of population inversion where you have more atoms up the hill than down the hill. So here it's natural to talk about a negative local beta. Okay, so that lines up, this gradient here lines up with a negative inverse temperature. Then if you go to this section here where the density is sort of higher down the hill than up the hill, that's kind of a more natural situation, and that's a positive local temperature. And so you're kind of oscillating about the infinite temperature limit, going between a negative beta and a positive beta. So this sort of system kind of created this wave of the energy density, or a wave of this beta by itself, just by falling down the hill. And at that point, once you've undergone the local thermalization, the density and the beta are kind of locked to each other in the system, okay? And they're out of phase by 90 degrees. So this beta is essentially the gradient of the density. So we've actually verified this process in the experiment. You can actually measure the local inverse temperature in the system. If you just look at individual sites, you can measure any two quantities like the singles density and the double density on a site. This ratio can give you the local inverse temperature, okay? And that's what we're seeing here, these orange points. So that's the beta backed out of these measurements, okay? And this, it sounds like something that would be hard to dream up, but actually some theorists had thought of these ideas before us, and those were explained in this beautiful paper by Achim Roche, this idea of creating this beta wave. Okay, so now you see that we have to relax not only this charge density wave, but also we have to relax the heat wave, right? The energy density wave. And so now we can start, since we've undergone the local thermalization, we can start talking about writing down a hydrodynamic model. And the first thing you would put into the hydrodynamic model is a heat current, right? So since you have energy densities that are varying in the system, gradients of the energy density would drive a heat current. And the proportionality constant between these two things is the thermal diffusivity, okay? So this heat current can be related to beta, the inverse temperature, in a high temperature expansion. They're just proportional to each other. So basically gradients of beta are what are driving this heat current. So the next thing you need in the hydrodynamics is energy and charge conservation. So the energy conservation law is written here. So basically if we look at the local energy density at any point, its rate of change comes about due to two contributions. One is you can have heat currents flowing into or out of that point. And then the other thing you can have is number currents in the system. So if you have an actual particle current, that can be converted to a heat current as the particles move down the gradient. You're converting internal energy into heat energy. And so this is essentially Joule heating here. Like this is I times V. V is the potential here is this F, okay? So in the limit of a very large gradient, we saw that the relaxation of these quantities N and the density and E are slow. So essentially you can set E dot to 0. And then these two things are equal to each other, the divergence of the heat current and the number current. So they're proportional to each other. A number current is the gradient of the heat current. Now, the heat current itself, I told you, was a gradient of beta. So now it's sort of a second derivative of beta. But if you go to the previous slide, this beta was also the derivative of the density, right? It's basically, you had to take the derivative of the density profile to get beta. So this is a third derivative of the density. And then we can add the number conservation, which is this law here, which tells us the rate of change of n is like a gradient of the particle current. So if you plug in the Jn from the previous equation, now you have a fourth derivative of the number current. And so now you get something that looks like a diffusion equation. N dot is some gradient of n, but it's not, the second derivative is the fourth derivative. And so that's what gives rise to this scaling of the time scale, the exponential time scale, like the fourth power of lambda. So you can see it here arising purely from this in the large tilt regime. And the proportionality constant turns out to be just the thermal diffusivity of the system. It no longer involves the number diffusivity. So essentially from this kind of experiment, you can back out the thermal diffusivity of the Hubbard model. And that's what we've done here. So I thought this is a cool system where you're seeing a very slow thermalization when the tilt is aligned with the lattice axis. But then if you go away from a lattice axis in a 2D system, then you expect to recover the Hilbert space fragmentation story I was telling you about, and that's subject of ongoing experiments we're doing. Or you could just simply go to a 1D system, and there again, you can just align the tilt with the 1D system, and you should see the same sort of physics. Okay, so before I switch maybe to the second topic of my talk for today, I'll just pose if you have any questions.
So it's actually like, what's with the time scales, like your model for the scaling with n to the fourth power that came from this effective picture with the two waves, but like what's the time scale to build up this local equilibrium and the two waves that then?
Yeah, so the waves are, the local equilibration time scale is very fast. So this is about 20 tunnel times. And then you saw the data for the relaxation, it's much longer, like we're talking about tunnel times or so. So you can kind of separate this into short time dynamics and then much later time dynamics, hydrodynamics.
Okay. Mm-hmm.
Mm-hmm. There are other questions? Okay, so in this next part of the talk, I'm going to now discuss another way to build constraints into a system. And this time it's going to be through Rydberg-dressing in a Fermi gas. Okay, so basically the Hamiltonian I'm going to show you how to engineer is what's known as a TV model. So this is a model where you have an itinerant Fermi gas, and at the same time it has off-site interactions in this lattice model. Okay, and you'll see again this would lead to some constrained dynamics. Okay, so obviously there's been a lot of activity in called atoms and molecules trying to engineer what we call long-range interactions. These are not long-range in the sense that condensed matter people talk about, but they're just long in the sense that our natural sort of range of the interactions between ground state atoms is typically like angstroms, so they're contact interactions in a lattice. But here we're trying to engineer off-site interactions in a lattice, so that requires going to interactions with a range more like a micron or so. And there are many different platforms people are exploring for that, including polar molecules, magnetic atoms, atoms in cavities, Rydberg atoms. So far, there are these systems which people use for simulating spin physics, like Rydberg atoms or atoms in cavities. So they're basically the constituents are just frozen in place, and they're interacting through these long-range interactions. But then there's also quantum gases, like quantum gases of, say, magnetic atoms like dysprosium or erbium, or polar molecules, where the constituents are moving around, they're itinerant. And one would like to reach strong interactions, strong long-range interactions in these systems. And so far that has been a challenge. With magnetic atoms, the off-site interactions tend to be very weak. With polar molecules, they look very promising, but there were so far issues with the lifetime that people are now working on fixing. And there's been very recent beautiful results on that from the group of Junier. So we're taking a different approach. So we're using Rydberg-dressing. So Rydberg-dressing is basically, we're going to start with the physics of Rydberg atoms, but now we're going to not excite the Rydberg atoms resonantly. We're just going to kind of create states which are dressed by the Rydberg atoms. by the Rydberg state. So sure, most of you are familiar with the physics of Rydberg atoms. So basically, these are atoms with where you excite the electron to very high n states, principal quantum number states. In particular, for us, we're working with lithium-6 with n equals 28. These states are pretty long-lived, so about 30 microseconds for our state. They have enormous radius, 60 nanometers, compared to the ground state atoms that's really big. And then they interact through strong van der Waals interactions. So if you take two atoms in this state at our lattice separation, the interaction energy is about 100 megahertz. Okay, so these numbers sound terrific, but they are not compatible at all with studying itinerant physics in these lattice systems. So the reason is, first, the lifetime is super short compared to the motional timescales. The typical tunneling timescales we have are milliseconds, so the Rydberg atoms would have decayed by then. And the interaction energy is just so much larger than the tunneling energy scale, which is typically on the kilohertz scale. So people have basically just focused on what's called the frozen gas regime in these systems, where the particles aren't moving at all during the Rydberg excitation. If you want to study itinerant physics, there was a proposal about a decade ago by in these papers here, where this idea of Rydberg-dressing was introduced. So basically, we're gonna couple the ground state to the Rydberg state very off-resonantly. So this delta is gonna be large compared to the Rabi frequency omega. And what that results in is basically a ground state with a small admixture of the Rydberg state, where the admixture is this beta, which is the ratio of the Rabi frequency to the detuning. And this beta is gonna be small compared to 1. So the advantage of working with this Rydberg state is, one, the lifetime is much longer, this Rydberg-dress state. So if you take the bare Rydberg lifetime, it's given by this, then we have an enhancement by a factor of 1 over beta squared. And this can be a pretty large enhancement that puts us into the lifetime of this dress state in the millisecond regime, where it can start to, the motional effects can have a role. Then the other interesting thing is that the interactions change. Now they're these soft core interactions between these stressed atoms. So those are basically flat over some region, and then they decay to 0. So the range of these interactions is typically micron scale, and their strength is controlled by the properties of the laser, like the Rabi frequency, the detuning. So so both of these, the range and the strength, are controlled in our experiments by properties of the laser and can be very dynamically. So Rydberg-dressing has been studied in experiments so far. There was these experiments from the group of Biederman, where they put two atoms in tweezers and they vary their separation, and they could map out these stressed potentials I was describing. There's also beautiful experiments from the Munich group, where they study this in a many-body setting, but in the frozen regime. So you put, say, a Mott insulator in one of two spin states, and then you can turn on the dressing light, and you can do many-body Ramsey interferometry, which can be used to map out these stressed potentials. Okay, so now what I would like to show in this work is, for the first time, getting out of this frozen gas regime with Rydberg-dressing. And the key advantage we have over these other experiments is we're working with lithium rather than heavy atoms like rubidium, which means that the tunneling time scale is pretty fast. And it's on the kilohertz scale for us, which is going to be fast compared to the decay rates and in the system. So we're doing a single photon excitation to a Rydberg 28p state using light deep in the UV at 230 nanometers. The Rabi frequencies we can reach are typically on the order of 10 megahertz, and the detunings we work with are in the range between 30 and 60 megahertz. So the first thing we did was we would like to extract the Rabi frequency, the coupling strength between the ground and the Rydberg atom. and the interactions between the atoms, the Rydberg-dressed interactions. So we essentially we used the same idea that the Munich group did. So this is this many-body Ramsey interferometry. So the idea here is we're going to start with an atom in state 1. So these are two hyperfine ground states. We're labeling 1 and 2. So state 1 is coupled to the Rydberg state off-resonantly. And then we're going to use a microwave pulse to prepare a superposition of states 1 and 2. Okay, so this is this Ramsey sequence. So we prepare a superposition of 1 and 2. And now we're going to pick up a differential phase shift during the evolution under the Rydberg, when we turn on the Rydberg-dressed laser. So this difference in the phase that's picked up between 1 and 2 is due to two contributions. One is there is a differential Stark shift due to the Rydberg-dressing laser. But then there's also the actual interactions between the atoms. So here we're predominantly dressing state 1, although in our case, because the splitting between those states is pretty small, it turns out also state 2 is dressed. And so both 1 and 2 are dressed, but 1 is more dressed than state 2. And so we have interactions between 2 atoms in state 1, 2 atoms in state 2, atoms in state 1 and state 2. And we need to keep track of all of these in the dynamics. So, okay, so the first thing we're going to do is just try to just measure the Rabi frequency, okay? Not even worry about the interactions. And if you noticed in the strength of the interaction between Rydberg-dressed atoms, that went as 1 over the detuning cubed, while the Stark shifts go as 1 over the detuning. So if you go to very large detuning, you can just forget about the interactions. The main thing that's causing the differential phase shift is the differential Stark shift, okay? So these first experiments we did where we just do a normal Ramsey sequence with a very large detuning, and then the Hamiltonian is essentially, you can think of it in the frozen regime as a spin Hamiltonian, where you have these Rydberg-dressed interactions, and then you have this differential Stark shift over here. And there's a collective light shift, which for a uniform system you can ignore. Yeah, so basically we're going to start in an initial state and then look at it after doing this pi over 2 dressing, pi over 2 pulse. And this is what we see after some evolution time. So there's, if you look in time, there's these Rabi fringes. And these Rabi fringes they have different frequencies depending on where you're looking in the cloud. So in the center of the cloud, it's a very fast Rabi frequency, very fast Ramsey fringe, and then as you go off, this Ramsey fringe goes down. And this is simply due to the variation of the Rabi frequency in the system. So we're essentially focusing the laser beam to a pretty tight waist on the order of 15 microns. And so that leads to a variation along the waist direction, which is this direction here of the Rabi frequency. And along the Rayleigh range direction, there is no variation at all. Okay, so this is this flat line here. That's along the Rayleigh range direction, the Ramsey frequency, fringe frequency doesn't change. And then along the orthogonal direction, it changes significantly. So that's how we measure our Rabi frequencies, because this differential Stark shift, if you know that you're detuning, you can use it to back out the Rabi frequency. Okay, so now let's go to the interactions. So to the leading term you saw in the evolution was the strong differential Stark shift. So we want to cancel those out. And what we do is a pi over 2 pi over 2 spin echo sequence. So this just gets rid of this effective magnetic field in the evolution. And then you're just left with the interaction term, okay? So now you can, any phases you pick up are due to the, just having interactions between the Rydberg-dressed atoms. And you can essentially probe this by looking at the density correlations in the system. Essentially, you want to say, if I have the spin here, I want to detect the field of the neighboring spin, so whether it's there or not. And so what or whether it's in spin up or spin down. So what we're looking at is we start from a band insulator with 1 fermion per site, and then we do the spin echo sequence and we extract the spin correlations. And if you look at in the short dressing time limit, the Munich group has shown that this correlation function goes as the square of the interaction between the Rydberg-dressed atoms. Okay, so you can essentially use it to map out, this correlation function can be used to map out the dressed potential. Okay, so here's some data. This is for different times. You can see the evolution of the spin correlations. The fact that you're seeing off-site stuff here tells you this is a long-range interaction in the spin correlations. Below is the theory. You can see there's they line up more or less, except for the fact that the experiment has this sort of large positive offset. And the positive offset in the correlation function is due to correlated atom loss during the evolution. So I'll discuss that a bit later. But this would lead to a positive correlation. And you can subtract that off, and then it agrees pretty well with the experiment. So this is this data in the experiment. So basically, we can back out Rydberg-dressed interactions, which are typically on the order of a few kilohertz. And so they compare favorably with the tunneling. So you can start to study the competition between the interactions and the tunneling in the system. Okay, so if you're familiar with Rydberg-dressing, one thing that has plagued all previous realizations is the short lifetimes in these Rydberg-dressed systems. And so you can start first by thinking about the single particle lifetime, which I told you is given by the usual bare lifetime divided by beta squared. But then when people started doing these experiments, they found that the lifetime is actually much shorter than that. And the reason is collective loss mechanisms. So you have a lot of particles in your system, you're dressing them, and there's collective effects that are leading to losses. So the typical process people consider limiting the lifetime is this black body induced avalanche loss that was studied in Munich and also the JQI. So there what you have is basically, you have this gas of Rydberg-dressed particles. One of the particles undergoes, it has this Rydberg admixture in it, so it can undergo a black body induced transition to a nearby Rydberg state of opposite parity. And then this other Rydberg, this contaminant atom at this point can interact with the other Rydberg-dressed atoms through resonant exchange interactions, because now it's in a different Rydberg state. This leads to a broadening of the line. So whereas your laser before used to be off resonant, now it can resonantly excite Rydberg atoms, which leads to an avalanche process, which typically just kicks out all the atoms in your sample. So you would expect the lifetime to be reduced by a factor of the number of atoms, because this basically you lose all your atoms when you have the first contaminant. And typically the solution is to work with smaller atom numbers, but still people have been limited by that. The Munich group has shown that if you work with one-dimensional systems, you can to some extent suppress this avalanche loss. In our experiments, we're actually working with a 2D system. And nevertheless, we still observe that we can get about 30% of the single particle lifetime for about 30 to 50 atoms in the system. So we don't quite understand what's going on there. The physics is pretty complicated, so we haven't tried to do any theory yet. But let me just show you some data. So here's the lifetime, so the decay of the atom number versus time. You can see it's clearly not exponential. So this means there's a density-dependent lifetime. So here it is extracted, the density-dependent lifetime. So this is the density on the lattice. And here I'm plotting the lifetime as a fraction of the single particle lifetime, okay? And you can see as we go to very low densities, we just almost approach the single particle lifetime. But as you go to higher densities, you start to have these collective effects. But what I want to emphasize is that we're not seeing sort of a total avalanche where we lose all the atoms. You would predict, for example, at a half-filled lattice, which is here, you would expect lifetimes on the order of like 6-7% of the single particle lifetime. We're seeing more like 30%. So it's an incomplete avalanche. And that's good news, because now if you look at our figure of merit, which is this interaction times the lifetime, we're getting typically figures of merit in the range of 20 to 30. Okay, so you can start to hope to look at coherent physics in the system. Okay, so since I was saying I wanted to look at itinerant physics, another concern is, does the lifetime change when you go from the frozen regime to an itinerant system? And that's been actually the subject of some controversy in theoretical papers, whether like motion should affect the lifetime if you have, say, two atoms landing on the same site. Is that a problem? And the results of our experiments is no, we do not see any effect of the tunneling on the lifetime. So if you, we've taken data from the frozen regime up to 2 kilohertz, the lifetimes just collapse on top of each other. Okay. So, okay, what sort of Hamiltonian can we engineer with this? So now what we're going to work with is a fermionic Hamiltonian. So we're going to just work with a spin polarized gas, just prepared in state 1. And we're going to Rydberg dress state 1. So this looks sort of like the Fermi Hubbard model, except now I don't need a spin index anymore because I'm working with a spin polarized gas. So you have tunneling between neighboring sites. And then we have these interactions. Because these are fermions, they can't hop on the same site. They're probably blocked. So I'm really just talking about off-site interactions here. And then on top of that, we have also the variation of the energy on the sites. Okay, and this variation of the energy is coming about both due to the lattice confinement potential, but also due to the actual dressing laser I said has a very large stark shift it exerts, right, along one direction. So we can simplify this Hamiltonian a bit further by realizing that actually our variation in the stark shift along this direction and the waste direction is so large that it completely suppresses the tunneling in that direction. So there's no tunneling along the y direction, just because of the very sharply varying potential due to the Rydberg-dressing light. But then along the Rayleigh range direction, we have free hopping, okay? So it just hops as if it's in a regular lattice. You don't see have a large confinement in that direction. So essentially you can boil this down to a mixed dimension TV model. So you have tunneling along X, but interactions along both directions. So it's as if you have basically coupled chain TV models, okay? A system that is made of coupled chains. All right, so of course, do you believe me? Let's do a quick check. So we've done these experiments where we start with a strip, let's say along Y, and then we see that it can spread normally in time, just like you would have in the absence of the dressing laser. If you start with a strip in the other direction, it's just completely not tunneling, as you can see here in the time evolution. So indeed, this seems to be a good description. Okay, so let's look at now quench dynamics in the system. So we have tunneling, we have interactions, we have a lifetime that's good compared to these time scales, so we can start to study itinerant physics. So let's first build our quantum sandcastle. So in this case, again, it's going to be a charge density wave. It's going to be a wave with period 4. So essentially the pattern is going to be, it doesn't have any spatial dependence in this direction along the y direction, but along the x direction, we're going to have basically a state that's 1, 1, 0, 0, 1, 1, 0, 0 repeating, okay? So, and then we have this so that's the ideal state we would like to build. In reality, the experiment is not quite so perfect. So the maximal density we reach is not quite 1. It's more like 0.7 or 0.8, okay? Then we're going to evolve this system under the TV model. And we're going to vary the interaction knob by varying the intensity of the dressing laser. So if you look at the non-interacting system, there you just expect ballistic expansion, okay? Just these wave functions will start to spread for the atoms, and what you get is basically this charge density wave disappears after a while, and then it actually revives with the opposite pattern. If you look here at the end, it kind of has the opposite pattern. Okay, so now let's introduce some interactions, stronger and stronger interactions. And you see in the limit of very strong interactions, this charge density wave is just frozen. It's not changing anymore. I mean, there's a little bit of motion, but not as much as the non-interacting case. So we can quantify all of this by, let's say, you can fit a sinusoid and look at how the amplitude of this is decaying. So here, for the non-interacting case, it flips sine, while for the interacting case, the amplitude decays, but not as quickly. And as we increase the strength of the interaction, there's more and more memory of the initial state. We can quantify this memory in terms of correlation function. So you can look at the overlaps essentially with the initial state. And here it is in pink for strong interactions. There's a strong memory of the initial state. In green, we kind of quickly go to the state that has the opposite pattern at this time. Okay. So, so why is this system stuck? Well, one thing that might worry you is, could we possibly have disorder in the system that's just Anderson localizing it and has nothing to do with the interactions? Well, that is a possibility because we do have these very large Rydberg-dressing, this very large Stark shifts due to the Rydberg-dressing light. They're actually the leading order effect before the interactions. So could there be disorder in the dressing beam? Well, the way to exclude that is just simply to work at the strongest interaction and then vary the density in the system. So we're just purely looking at interaction effects then. So we're varying the density, and we see as we go to lower density, at high densities, we get this frozen state, but then at lower densities, we see the system just evolve as you would expect for a non-interacting system. Or even though here it is interacting, it's just that the density is low. Okay. So what's the explanation here? Well, the explanation is pretty simple. So you have this 1100 pattern along the non-frozen, along the tunneling direction. And if you think about the limit T over V going to 0, so the interaction is becoming really strong, then you can't have these fermions hop over because there's a constraint. You can't break this bond because there's no tunneling energy. The tunneling energy is small, so you can't convert the V into a tunneling energy. So essentially, we have a frozen state. This is a frozen state like a quantum scar where the number of bonds is conserved. So both the charge in the system and the number of bonds is conserved. And just like I was telling you earlier with this fragmentation story, the sectors can be labeled with the charge and the number of bonds. And then even within each of these conserved sectors with labeled by the conserved quantities, you have subsectors. And these subsectors are labeled by the delocalized degrees of freedom. So this is explained in this paper studying this model by Pullman. So these are basically, you imagine starting from a frozen state and then you introduce a defect. This defect is free to move around, and the number of such defects can be used to label these subsectors, and there's an exponentially large number of them. So in fact, if you just consider states with a single mover, if you add this order, you can localize them. It's just an Anderson localization process. You can also consider a finite density of movers, and then you'll have a many-body localization of these. And basically, the constraints here act in a way to lower the disorder required for the many-body localization. So I think this is, again, a very interesting system where there's an interplay between the constraints and the dynamics. Just like the Rydberg systems that were studied in Misha's group and this tilted Hubbard system I just described. So since this is a new platform where for the first time we're seeing strong offsite interactions interplaying with tunneling, let me just give an outlook on that. So one can imagine also going not just to a spin polarized gas, but adding spin states. So then you would have an extended Hubbard model with interesting dynamics itself. Of course, the challenge is to kind of improve the coherence of these systems. There are many experimental avenues towards that. One way would be to increase the Rabi frequencies. So if you just put a build-up cavity, for example, around the system, you can enhance this Rabi frequency on the order of 10 to 20. That would also allow you to detune further, which shrinks the facilitation radii, which are involved in these avalanche processes. So one would also expect a longer lifetime because of that. So I think with these improvements, one can hope to get to a system that's maybe a factor of 30 or so more coherent than we've demonstrated so far. Okay, so that brings me to the end of my talk. Let me just quickly summarize. We've basically studied two models, engineered two models which have kinetic constraints in them. So far, we haven't yet started exploring the non-ergodicity as a result of these constraints, but we've seen already some interesting thermalization, slow thermalization behavior in the Fermi Hubbard model with tilt. So there we saw this subdiffusive charge dynamics, and we were able to back out from our measurements the thermal diffusivity. We, for the first time now, realized a lattice model with strong non-local interactions using this Rydberg-dressing. And again, this TV model turns out to be a constrained system with constrained dynamics that shatter the Hilbert space and can lead to very interesting non-ergodic dynamics. So with that, let me just thank the members of my group who've led this work, Elmer Guardado-Sanchez and Ben Spar. And we've had a lot of theory support from David Hughes at Princeton and Alexei Gorshkov's group at Maryland. And thank you very much for your attention.
Thank you very much for this very nice talk, Waseem. Mm-hmm. Other questions? So then you can just like unmute and talk. So maybe let me start with the question, like this explanation that you gave in the end for your Rydberg dress system. This is really like that was kind of like a 1D explanation, right? That you can that the bonds are conserved.
Yeah.
So do you think there's like is it just like I mean, how big are the differences like compared to the system that you really have in 2D?
Yeah, so we actually the paper is going to be on the archive next week. So the 1D does not explain what we're seeing exactly. You have to go to 2D to have better agreement. Now our modeling is still like far from perfect. We're not taking into account atom loss. We are taking into account the imperfect state preparation and so on. But there's a clear evidence that the 2D is different from 1D. I mean, as you might expect, if you have some defects in the preparation, the fact that you're in a two-dimensional system, you also have extra bonds in the other direction. That makes the system even more robust to this decay.
Okay, more questions? Well, I also have another one, like on the spin echo sequence that you have, like how robust is this with respect to like dephasing effects and other decoherence like mechanisms that you might have in the system? Like how exactly can you like cancel out the Stark shift you were talking about?
I mean, the biggest problem we usually face is fluctuations of the intensity of the dressing laser, but we seem to have those under control. I mean, all I can point out is the agreement between the theoretical modeling and the data. So it seems to be describing what's going on pretty well.
Okay. Mm-hmm.
And once we basically in the beginning we had a lot of issues with. I mean, this 230 nanometer laser, it's a headache wavelength to work at. You have to kind of quadruple a diode laser. So you need like two cavities, and with cavities, you can have a lot of intensity noise in the system because of the fluctuations of the cavities. So once we were able to stabilize the intensity of the system pretty well by adding some electro-optic modulators, it seems to be robust.
That's a very nice technique, I think.
I mean, the technique is the same technique that was probably Ahmed was involved in this. That's the technique introduced by the Munich group.
Okay. Last chance to ask more questions. Otherwise, I would like to thank Waseem again and announce like next week we'll have Peter Schaus talking also, I think, on some Rydberg physics, maybe.